Okay, now that we've seen a dynamic programming problem in detail with the edit distance, I want to start to look at some other problems that can be solved efficiently with dynamic programming. And one of them is making change, which is kind of neat. So if I have the coins 1 cent, 5 cent, 10 cent, and 25 cent, what are the fewest number, or what is this fewest number of coins I need to make change? So as an example, let's say my amount is 75. Well then I need 3, which is 3 quarters, right? 3 times 25 cents. If my amount is 11, then I can get away with 2. So I have 1 10 cent plus 1 cent. If my amount is 23, then I guess I can do 5. So 5, 2 10 cent plus 3 1 cent. Right? So that's the problem. And I'll check all these in a moment once I make the code. But how did I do that? And can I train a computer to do that in a smart way? So let's break this problem down recursively first. So I'll say def min coins needed. I'll pass along 2 parameters, what the coin types are, that's going to be a list of coins, and the amount I'm trying to make. Let me call it AMT for short. Okay. So I have 2 parameters. The first parameter is a list of all possible coins values. And then amount is an int. It's the change I'm trying to make. And for now, I'm just going to return the min number that I needed, not what they are, but just the minimum that I need. And I'll show you how to tweak it in a moment to actually figure out what these are. But the minimum number of coins needed to make change. Okay, so that's my goal with this method. So let me think recursively about this actually. I'm going to start from the top down. So I'm going to start with the amount, start seeing, okay, what if I add this coin? What do I have left? What if I add this coin? What do I have left? So the base case is actually fairly simple. If we get lucky and the amount we're looking for actually happens to be one of the coins we have available to us, then we're done. So I'll say if the amount happens to be one of the coins. So if amount is in the coins list, return 1. Okay, so that's the base case. All right, but otherwise I have to do a little work. So what I'm going to do is first say, well, look, let me come up with sort of the worst that I could do first. That's if, I'll say min coins equals, the worst I could do is actually if every single coin is a 1 cent. So let me assume that 1 cent is always in the list, just to make it easier on myself for now. So the worst I can do is make every single coin 1 cent. And I'm going to need as many as there are amount to do that. Okay, but let's see if I can do better. Now think about this recursively. I'm going to try each coin in turn. So I'll say for C in coins. So let me say smaller, or let me say SMAMT for smaller amount. That will be equal to the amount minus the coin. That's what I have left. So if this happens to be a positive number, that means that I took the coin away and I still have some stuff left. So what I'll say is, and I know that this can't be 0 because I would have already caught that already. So I'll say if the smaller amount is greater than 0, then what I'll do is I will actually do a recursive call here. I'll say min C. So the min that I need here is well, I'm going to use the coin C, and I'm going to see what's the minimum amount of coins. Here's where the recursion comes in. What's the minimum amount of coins that I need for this smaller amount? Okay. So figure out what's the minimum coins I need for the smaller amount. Add 1 coin on because I'm actually going to use this coin C. And if that happens to be less than the minimum that I've seen so far, then I will reset the min accordingly. So this will do that. This will say the minimum number of coins that I've needed so far is the minimum among what I've seen so far, and this new option that I've computed, supposing that I use the coin C and fill in what's left. Okay, so once we're finished looking at all possibilities, then we can return the min coins here. So that's what we do recursively. We consider each coin in turn, and then try to make change with the rest. And see, did we do better than what we've seen so far? Okay, now this is not going to be very efficient. We've got a problem because, in our example where we have 4 different types of coins, we're going to branch out in the recursion 4 times. So this is going to be like a 4 to the n algorithm, where n is the amount that I'm trying to make change for. So that is going to be very slow. But we can memoize, right? We always try it when we're like, okay, this recursion is going to be crazy, but we're going to reuse a lot of stuff. So let's just remember some of the results. So this is going to be a dictionary from an amount to the minimum number of coins needed to make that amount. Okay, so I'll just do that. So that's my memory. By the way, this is called a default parameter. So if I don't pass in a third parameter, it's going to make this the empty dictionary. Okay, so that makes it a little easier to call at the beginning. So let me add my memory to this recursive call. And here's what I need to do, actually. So what I should check is, so if this is not in the memory yet, then I will, so if this amount of money that I need to make change of has not been seen yet, then I do need to actually do the recursive call. So I'll say memory smamt equals min coins needed, that. Okay, now at this point, I know that it's in memory. If it wasn't, I'm going to do the recursive call. If it was, I didn't have to do it. I skip this, and I can pull it out of memory. Okay. So this is a little speed up I did. Not that much code, but now I'm going to remember stuff using a dictionary. So let's see if this works. Fingers crossed. So what I'll do is print min coins needed. Let me try that first example. 7. So my coins are 1, 5, 10, 25. Let me see, trying to make 75 here. Min coins needed. There we go. 3. Okay, that worked. So far, so good. All right, let's try 11. That should be 2, right? Looking good. Let's try 23. 5. Okay, seems like it's working. I mean, I should test it more rigorously, but for now, that seems good. I'm curious about something though. Which values did I need to consider in the solution of making this? So let me actually create a memory that I pass along, and I will examine this memory at the end. So let's say that I'm making, for example, 75. Okay, so this is pretty interesting. Let me actually, let's see, 4K in sorted keys. I think that'll do it. I'm going to print these out in order. Okay, so actually I computed a bunch of intermediate answers, right? So I found, actually that's interesting, it took 8 coins to make 74 cents. Maybe I'll keep that example. 4 coins to make 70 cents, let me see, what would that be? I guess you can get up to 50 with 2, and then you have to take, then you have to take 2 dimes, okay. But anyway, what we're seeing here is we computed a bunch of intermediate results, and actually, as far as I can see, are we even missing any? I mean, I sort of on the fly figured out which ones I needed to compute, but it looks like I considered almost everything. So another thing you could do is a bottom-up approach, actually, where you, I mean, I'll keep this here, but let's try something else where, and this is a little more like the dynamic programming approach that we did for the edit distance, where from the bottom up we consider the smallest strings and then we use them to build up bigger and bigger solutions. So maybe what we can do is start off with 1 cent, 2 cent, 3 cent, 4 cent, do the same kind of recurrence relation here, but do bottom up instead of top down. So let me do that now, because it seems like I'm using almost everything anyway, so I might as well just go from 1 cent up to my amount. Alright, so let's make this iterative method. So it's going to have the same parameters, except I'm not going to need a memory, because the memory is going to be there as I go along. So I'll call this min coins needed dime for dynamic programming. And so now I'm actually going to, I could define mem, but I'll make it a list. So I'll say mem is equal to 0 times amount plus 1. So I'm going to make a list with amount plus 1 elements, which is going to store the minimum number of coins that I need to make a particular amount. So for example, mem at index 10 is minimum number needed to make 10 cents, for example. Okay. So what I can do is I can go bottom up, like I said. So I'm going to loop from, so I guess I'll say for amount I in range 1 amount plus 1. So that will go from 1 cent up to amount cents. And let's see how much of this code I can repurpose. So I'm going to copy and paste this code, but I'm going to change it, recognizing that I'm filling in this memory from the bottom up. And I'm actually not doing recursion anymore. Everything's going to be iterative. So what I can say is if the amount I, so it starts off with 1, then 2, then 3. If that happens to be one of the coins, then I can say that I'll remember that that cost 1. Okay. Otherwise, I can say, well, the minimum I think I need, the worst case, it's going to be the amount I that I'm looking at. Let me check all the coins. So here's the smaller amount. Now, here's what's interesting. Because I'm going from the bottom up, I know that I've processed everything before this. So I know that this is in the memory, actually. So that's kind of neat. So I can say min c is equal to 1 plus the memory of the smaller amount. And just compute it that way. Okay, now instead of return min coins, I'm just going to remember that. And I think that's all I need to do. So let me check this. So let me look back at this example again. This should still give me 3. So just to change this, I want to check the dime one. Oops, I didn't. Okay. So, it looks like I'm making a mistake. So I meant to return the last element, right? The last element is actually the amount that I'm looking for. Everything before that is just stuff I filled in before that. Let's see. Now, but I can see that the whole list doesn't look quite right. I'm saying that I need basically 1 coin for everything. So let me check and see where I messed this up. Okay, so min c, min coins is equal to the min. Okay, so I'm imagining that I held out this coin c, and I keep taking the min. Okay, that's strange because that looks right to me. Okay, so we're going through, we're saying, is this amount in the coins? Let me just make sure I got all my variables right. Min coins equals the amount I. I meant to say the amount I minus C. There we go. Okay. Now that seems right. And actually, maybe let's check let's check, kind of spot check some of the values here. So I'll say 4K in range. We don't need to do that. Okay, no, I can spot check. Can't make up my mind. Yeah, just let me print the whole memory here. Let's see, it says, yeah, does it take 8 to make 74? Or 74 up here? So I'm just going to spot check it. Yeah, that takes 8. Okay. So anyway, it seems like this is working. Let me just test the other ones again. So I'm going to do 11. That takes 2. 23. That should take 5. Okay. So cool. This works. And I actually got rid of the recursion, which is really nice. Now, what if I want to remember what I did? Well, I can actually do something very similar to what I did with the edit distance. Let me make another list here. I'll call this optimal. And don't worry about the syntax too much. This is called a list comprehension. This is how you make a list of lists, where each list is unique. I had you do this with a loop in assignment 1. But anyway, this is a quicker way to do it. Okay, so what I'm going to do is once I figure out what the minimum number of coins is to make a particular amount I, what I'll do is I'll loop through all the coins again and I'll see which ones actually achieved this cost. So I'll say if min C is equal to the min coins that I found, then I will append this coin to the list. Okay. So let me actually spot check this. So if I'm looking for 75, I know that that should be made up of 3 25-cent coins. So the first coin I should see is a 25-cent coin. Let me print this out and see if that's the case. So I'll print optimal amount. Didn't like that. I meant to say if min C is equal. Let's see. Looks like it's saying nothing, which is... Oh no, I meant to say optimal at index amount I, dependency. Okay. I'm saying that for this amount, here's a coin that you can use in an optimal way of making change. Okay, so I got it that time. Now, how do I get them all? Well, I do the same kind of recursive backtracing thing. So I'll start this and I'll have